It is part 2 of section 8.3, AGNES, Agglomerative Clustering. AGNES begins from the bottom of the clustering tree where each point is considered as a singleton cluster. And in each iteration step, AGNES merges two closest clusters. So AGNES must be given with a similarity measure, which measures the distance between two clusters. Here we have a question. How do we measure the similarity or dissimilarity between two groups of observations? To answer the question, various cluster agglomeration methods have been developed. The most popular ones are single linkage, complete linkage, group linkage, centroid linkage, and Wa's minimum variance. Let's go through one by one. In single linkage, the similarity is measured with the closest pair. The distance between two clusters, G and H, is defined in this way. I and J are selected from G and H, respectively, and among the distances, and we are choosing the minimum. So it is using the closest pair. With this linkage, here the cluster tends to have some the loose long clusters, which is called the chaining. Now for complete linkage, the measure is along with the farthest pair. The distance between two clusters G and H is defined with a maximum of those distances from G and H. So here, now this linkage, complete linkage, has opposite problem. It might not merge close groups because of outlier points. For example, two clusters are close to each other. However, each one has an outlier far away. Then these two clusters will not be merged. However, it tends to produce more compact clusters. Now let's go to third one, group linkage, group averaging. Here, as the name says, try to use averaging from two groups and G and H clusters. We try to measure distance, every possible combination, measure distance, and try to make averaging. This is a natural compromise. It's working well in most cases. And centroid linkage is now using the centroids of two clusters. We try to measure the distance. Also, it is reasonably okay, working well. Now, finally, the Wa's minimum variance is trying to minimize the total within cluster variance. More precisely, we can say that the method finds the pair of clusters that leads to minimum increase in the total within cluster variance. Now, when you are using the sum of squared error, then it is basically sum of variances from each cluster. Okay, I'll try to explain this one a little bit here. Okay, now assume we have 3 clusters here, one, and another one here, and another one here. So that if you try to measure the sum of squared error, then from the center of each cluster, we are measuring variance here within each cluster. And then these variances are summed, then that is the sum of squared error. So once you try to merge two clusters, then usually the variance will increase. Rather than these three clusters, if you try to merge, for example, these two clusters, then new cluster center will be computed here. And from this one, the point over there is farther, so that the variance will be increased. Now also the same, if you try to merge these two, then again the variance will be increased a lot. However, if you try to merge these two, then new center will be obtained, and then the variance, of course, the total variance is increasing. However, the amount of increase is minimum, smaller than the other cases. So in this way, the Watt's minimum variance is trying to find the two clusters such that the cluster variance is increased minimum. That's the idea of Watt's minimum variance. Okay, here for AGNES, we'll consider its interpretability and visualization. Here, each level of the resulting tree is a segmentation of data, and the algorithm, AGNES, results in a sequence of the clustering. It's up to the user to choose a natural clustering from this sequence. Now, we can visualize the sequence along with the dendrogram. Agglomerative clustering is monotonic, and here the similarity between merged clusters are monotone decreasing with the level of merge. So if you look at the dendrogram, then in lower level here, around the bottom, here, each element is a cluster. So that if you try to measure variance, then because it's a singleton cluster, the variance will be 0. Now, if you merge in the beginning, for instance, E and F, then now center will be gotten, and here the variance will increase. So like that, here, the similarity is decreasing monotonically along that direction. And that means that dissimilarity is increasing. In fact, rather than dissimilarity, we may use the variance, then it's easy to understand. Here, along that up direction, here, along that direction, the variance is increasing. Okay. And now dendrogram is plotting each merge at the dissimilarity between the two merged groups, and also it provides an interpretable visualization of the algorithm. And by using here horizontal line, you can realize the clustering. For example, if you are making this horizontal line, then there must be two vertical lines, and then that means that practically you have two clusters, and AB is one side and the other ones are on the other side. If you try to make a horizontal line, for example, here, like that, then there must be 3 clusters, and AB is 1 for that, and then C is a singleton cluster, and DEF is another cluster like that, right? So in this way, user can choose a horizontal line that is a level of variance, and also can find the clustering. Okay, and also this dendrogram is really good, useful summarization tool. So that's the reason, partial reason that hierarchical clustering is so popular. Here we have a remark. The height of the dendrogram indicates the order in which the clusters were joined. And here, if it's lower than in earlier joined, and here in upper portion, then it's later joined. And also it reflects the distance between the clusters. And so that eventually, once you try to measure the variance, then variances increase. Okay. The greater the difference in height, the more dissimilarity. Okay. And here observations are allocated to clusters by drawing a horizontal line through the dendrogram. Okay, we already considered that. Now we'll see some examples. Now, along with a single linkage, the data points are now clustered by using the AGNES. So in the beginning here, 3 and 6 are joined, and then 2 and 5 are merged. And after that, here now these 2 are merged, and point 4 merged here, and then point 1 is now merged to become a single cluster, along with a single linkage. And this single linkage is a way of measuring cluster distance. But here now, closest pair is used so that anyway, up to this point, it is loose, the chain, long cluster can be made. And here, okay, here it can be it can make non-spherical, non-convex clusters. If we want to say this is advantage, then it is a kind of advantage. But this advantage is chaining like this, and long loose cluster can be made. And now, once we measure the distance, the cluster distance by using complete linkage, so the farthest pair is used for the cluster distance, then here in the beginning, the lowest merge is between 3 and 6, and next merge is, second merge is in 2 and 5, and then third merge is now 3, 6, and now 0.4, and later on, and 2, 5 cluster, and here 0.1 are merged, and then later on, these 2 big clusters are merged. Okay, and with a complete linkage is a more robust against the noise, and there's no chaining now here, and also it has a tendency to break large clusters. The reason is that there's some bias, there's some outlier or noise, then because there's a farthest pair distance measure, some near 2 clusters may not be merged. So it looks like a brick large clusters. Okay. Okay, here, along with the average linkage, here the performance is almost the same. But anyway, this is good compromise. Okay. Here, first 3 and 6 are merged and 4 are merged to 36. And then, okay, after 2, 5 merged and this is merged. And then these two are merged and here and then number 1 point is merged finally. Okay. Okay, here those are examples, and for what's minimum variance method, we consider this one. Similarity of two clusters is based on the increase in squared error when two clusters are merged. And so that try to choose two clusters which increases the variance minimum. And along with this strategy, the method is less susceptible and sensitive to the noise and outliers. And also it is biased toward globular clusters. That means that it's working much better when the clusters are globular shape. That is a hierarchical analog of the k-means, and particularly it can be used to initialize the k-means. And k-means works with a global objective function. People prefer global objective function. Okay, that's the end of the section. Thank you.